Welcome everyone to the ELEC2134 crash course. I'm joined by Shai. Shai, do you want to introduce yourself?
Yep. Hi, everyone. People watching both online and on YouTube later on. My name is Shai. Some of you have had for lab demoing, and I'm going to be hosting the crash course today. I've prepared some questions for us today, and I will share the solutions at the end of the crash course in case you want to, because most likely my working will be very messy anyway. So just in case you guys want to look at the proper solutions, I will share that at the end of the crash course.
Excellent. Okay, so we'll dive in. Does anyone have any questions before we get going? Okay, no worries. Thanks, Vincent. Thanks, Alex. Let's do it.
Okay. So I prepared a bunch of questions. Let me see which one I want to start with first. I think I'll start with a transient analysis question, because I noticed during Lab 5, a lot of people were kind of unsure about how to go about it, especially with the deriving the differential equations, because it's not always a step-by-step process, which is why sometimes I find the Laplace transform is a bit more it's a bit easier to follow, right? Because it's essentially just analyze a circuit and then do some partial fractions and you're done. But I think it's important to be comfortable with both methods. So that's why I'm going to go through both methods today. I've got one question which is done by the differential equations method, and actually I've got a couple with the Laplace transform, because I know that Julian didn't really go over how to account for initial conditions with the Laplace transform. So I thought that would be very useful to cover. So I'll just get the question up and I'll share my screen. I'll also turn my camera off because I have to put my tablet on the flat on the table, so you guys wouldn't be able to see me. Okay.
I can do this.
True. Okay, share. Okay, so you guys should be able to see that. Okay, so this question is from 2011, I believe, which is actually quite a hard past paper. I would recommend. They're on the ELSOC drive, I believe, the pre-2014 ones. So this one is quite a difficult past paper, in my opinion. It has a lot of questions and the values are not very nice. So I mean, you can already see they're all like decimal values. So yeah, yeah. This question is quite long, I believe. But we'll go through it. So all it is it's a RLC circuit. The circuit has a switch that is open at t equals 0. It wants you to show that these are the characteristic roots of the equation, so minus 35.86, minus 0.349. And then it wants us to find the current through the resistor for t greater than 0. And it specifically asks to not use the Laplace transform. So it's pretty helpful. The reason why I'm going through both methods today is because sometimes questions will want you to do one method and sometimes they prefer the other. So it's really a 50-50. You know, you're going to have to be able to be comfortable with both of them if you want to excel at these types of questions. Okay, so how would I start this question? Well, I would probably consider the t less than 0 circuit first. So consider the circuit when it has been closed when it has been just in this position for a very long time. So the switch is closed. For a steady state, we're assuming infinite time, as silly as that sounds. So I'll just quickly draw the circuit. I do find that it's helpful drawing the circuit, even though it's mainly just redrawing what they've got on the question. But okay, you've got a 10 ohm resistor there, got an 8 ohm there. This capacitor will be open circuit and the inductor will be short circuited. I've then got a 12 ohm resistor there. Okay, so far so good, nothing crazy yet. So what I typically look for when I'm looking at this circuit is any voltages across capacitors and any currents going through inductors. Yeah, that's what I'm mainly looking for. So essentially just finding the initial conditions. In this case, the current that's going through the inductor is also the current that's going through the resistor. So we can just kind of say, well, I'll call it I with a subscript of R of T, or I'll say of 0. And I hope you realize that this is just a current divider, right? Because you've got a 10 amp current source, which is in parallel with two 10 ohm resistors and one 20 ohm resistor if you combine these in series, right? So ELEC 111 knowledge, you guys. So 20. Oh, sorry, it should be 1 on 20. Because the current divider equation is the annoying one where you've got the fractions. Anyways, so I'll just put that into my calculator. And we should get 2. Awesome. That's a nice value. So 2 amps. Great. So that's the, you can also think of that as the current through the inductor at t equals 0. Only thing left to find is the capacitor voltage, right? The reason we don't, yeah, okay, yeah, the capacitor voltage. So I'll just call it VC of 0, which is, I mean, if you're looking across these terminals, then it's just going to be 12 times IR of 0. If you just do Ohm's law, so it would just be 24. Oops, 24 volts. Cool. So yeah, pretty simple. I think it's nice that you do this before because it kind of gives you a because this process is the same no matter what the question is, and it just kind of gets you into the question. I don't know. The second step after you consider the steady state circuit is obviously you consider t greater than 0, and by t greater than 0 I mean the transient. Okay, so and also I'm going to redraw the circuit because that very much helps. So the switch opens, so we're no longer going to have a 10 ohm resistor in parallel. Yeah, so we're going to have that 10 ohm there, and then we're going to have a capacitor in parallel. Oh, and an inductor. Yeah, there we go. Okay, not the best diagram. I've drawn better, but okay. The capacitor is 0.4 farads and the inductor is 0.5. Oh, I've also missed a resistor, Henry. Yeah, I've missed an 8 ohm. Okay. Before I go ahead, I'm going to simplify the circuit a little bit because if you notice, I've got a current source which is in parallel with a resistor, and just so that I avoid as many having as many nodes / meshes as possible, I'm just gonna source transform it. So it's gonna turn into a 100 amp voltage source, right? Because 10 times 10, and you're gonna wind up with a 10 ohm in series with the 8 ohm, which combines to 18 ohms. Then you've got the inductor, got the capacitor, and a 12 ohm in parallel. And this is IR of t. Okay, great. I'm actually going to call it IR with it like a capital, so that I can avoid writing the T's every single time. Okay. Guess the next step is to solve the differential or derive the differential equations. So I think I'm just going to do a KVL in the first mesh right here. So that means, yeah. Okay. Oh, and I'm taking the capacitor voltage as this. Cool beans. So we've got minus 100 plus 18 IR plus, now, right, I'm going to say VC because we're just moving across the voltage of the capacitor. So I'm going to go call it VC. And plus 0. Right, so that's just simple KVL around the loop. So what we're looking for is to just get an expression which is only in terms of IR, right? Since that's what we're solving. So majority of the pain from solving these or deriving these differential equations is trying to get everything in terms of one variable. At least in my opinion, that's probably the biggest pain. So I'm going to write down, and we're going to get expressions for these in terms of IR using the differential equations of capacitors and inductors. So what do I start? Okay, I'll write down 3 equations. Okay, so number 1, the current through the inductor is equivalent to the current to the capacitor plus the current plus IR, right? That's just simple nodal, right? So equals C. And so the current through the capacitor, right? That is C dV on dt, right? Just from the equation, the capacitor equation. So we can instantly just say it's that. And then plus I of R. You might be going, well, Shai, why did you write down that equation? Well, it's going to be useful in a second. I know we've got voltages here, but it will be useful in just a second. Second equation I'm going to write is the voltage through the inductor. Sorry. Yeah, no, voltage through the inductor. Oh, yeah. Oh, sorry. Oh, right. Yep. Sorry, I don't know. I get notified for the questions. Oh, well. Yeah. That's all good. Did you want to take a screenshot or something? I can also post it in the chat if you guys want. Yeah. All right, all good. All right. So for those of you who, I don't know how many people joined since, but there's quite a lot, quite a few. So all I've done is I've just found the initial conditions for this transient circuit. Right now I'm in the process of deriving the differential equation for the characteristic equation of the question, and then I've just done a mesh. That's it. That's all I've done. So back to what I was saying. So I'm going to do the voltage through the inductor, which is L di dt, right? So L d I L over dt. Okay. And one last one, which is just VC is equal to 12 IR, remember? If you well, it just goes back to what I was saying before with if you consider just this voltage, it's just Ohm's law. So with these 3 equations, you can pretty much derive the full differential equation that you end up with. So I'm going to do that right now. And it's just a matter of kind of subbing in these 3 equations into wherever you can to get things in terms of IR. Okay. Oh, Oh, actually, I've made a mistake. I just realized this should be IL, because that's this current here is not it's not the current that goes to the resistor. It's the current that goes to the inductor. I'm going to call it IL. Yeah, sorry about that. Okay, so minus 100 plus 18. And now I'm going to use equation 1, right, where IL is IC plus IR. So C times dV over dt plus IR the voltage across the inductor is just 12 IR, so that's easy. The voltage through the inductor is L dIL on dt. And that whole thing is equal to 0. Okay. We're not there yet. You've got quite a ways to go. So I'm going to keep simplifying it. Now, I hope you realize that. So dVc on dt, as in the Vc being the voltage across the inductor, I'm just going to use equation 3 to be like, this is
18 times IR.
Oh, yeah, I fixed that. Yeah, good catch, Alex. Yes, it should be IL, yes, not IR. So yep, so I'm just going to use equation 3. So it's C times 12 dIR on dt. Cool, that's fine. Plus IR. Plus 12 IR, that doesn't change. Plus LDIL on dt. Now, LDIL on dt, I'm just going to use equation 1. Oops, d on dt of where IL is IC plus IR. So again, same thing, C times 12 dir on dt plus IR. Okay. Oh, and that entire thing equals 0. So essentially, I've got everything in terms of IR at the moment. Yes, it looks a little bit messy, and we're going to have to do some cleaning up. But in pretty much a couple of steps, I've converted from, having 3 different variables to everything in terms of IR. Now it's just a matter of cleaning everything up. So minus 100 plus, I'm going to start subbing stuff in. So 18 times C, which is 0.4 times 12, that gives me 86.4. DIR on dt. So DIR on dt plus 18 IR plus 12 IR. 18 plus 12 is 30, so I'm just going to write 30. Plus L times that. So 0.4 times the derivative of that. So that should be 12 times C times d squared IR on dt, right? Because you're taking the derivative of a derivative. So that just gives you the second order derivative. And then dir on dt equals 0. Great, awesome. I'm going to move the 100 to the other side and then just go dir on dt plus 30 IR plus, okay, we've got 0.4 times 12, 0.5, 2.4 d squared IR on dt squared plus 0.4 dir on dt equals 0. Okay, whew, that took a lot, but it's all okay algebra. I'm going to just collect like terms and then divide by 2.4. So d squared IR on dt squared plus 30 divided by 2.4 is 12.5. 12.5 IR plus 86.4 plus 0.4, and then that divided by 2.4 gives me about 36.2, I would say. I'll say 36.2. The IR over dt equals 0. Cool. That is our characteristic equation. And actually, I'm just gonna move these just so that it's in like the proper form. Should the right? Oh yeah, you're right. I was gonna fix that. The right-hand side should be 100. Yep. It's good that you guys are calling me out. Okay. So that sounds good so far. All we have to do is find what type of characteristic equation it is. So, God, what step am I up to? All right, 3. So, type of solution. So you can either have overdamped, underdamped, critically, or undamped. And I think they usually like to give either overdamped or underdamped. I don't think you'll deal too much with the critically damped cases, but I guess it's, well, since it's open book, you might as well have like a formula sheet with all of the like damping cases. I can also share my formula sheet that I had for 2134. It's got pretty much everything on it, if you guys are curious. Okay, so my alpha is half of 36.2, so 18.1. My omega n is, forgot what the name for it is. It's like I just know the damped frequency. I forgot what the name for this. Natural frequency? Yeah, okay. Thanks, Peter. It's just a root of 12.5. So root of 12.5 is about 3.54. Great. I am doing some rounding, and it's okay. You can round. They're not going to be super strict. So because alpha is a lot bigger than omega n, then this is going to be overdamped, right? And the solutions are going to be minus alpha minus omega damped and minus alpha plus omega damped, where omega damped is, or the damped frequency is the square root of a squared minus omega n squared. Yeah, so if I just do that really quick, that should give me about 17.75. I hope you guys are following. So, and then if you just plug all of that into the calculator, you get minus 35.85 and what else? Minus 0.35. Maybe I shouldn't have rounded because I think they got something that was a bit more exact. Yeah. Oh yeah, that's just a result of me rounding, so don't worry about it. I'm just trying to be quick. But you can see I'm mostly right, if not for some like rounding errors. Just confirming we'd get the same answers for S1, S2 if we use the quadratic formula, right? Yeah, that should be fine. Yeah. So really you can solve the quadratic formula. You can write it all as in like s squared plus 36.2s plus 12.5 equals 0, and that will be right. Yep, all good. Yep. All right, that's good. Yeah, I mean, you should like verify your answers. Like if you're not sure, you can try solving it through the quadratic equation and just making sure that your answers are the same. That works. Okay. Right. So what we have now is the solutions, and because it's overdamped, if you remember the equation, your solution will be some combination of exponentials where the power in the exponentials are their roots. So minus 35.85t plus a2 e to the minus 0.35 t. Okay. So that's your natural response. You also have to consider the forced response. So, which is the steady state part. So we're gonna just assume IR of t is a constant value, and then if we plug that solution into our characteristic equation, noting that the derivative of a constant with respect to time is 0, then we just get 12.5k equals 100, which gives us k equals 8. Oh, hang on. Oh, that should not be 100. Should be 100 divided by 2.4. Just realized. So 41.67. Yep, sorry about that. 41.67. And that gives us k equals 3.33. 3.3 repeater. So yeah, sorry about that. All that's changed is the constant, which only affects the forced response. Okay. All we have to do now is just solve for the constants, which admittedly is sometimes a very annoying process. So solve A1 and A2, and then you'd pretty much be done. So one way you can, so you solve for these by just considering the t equals 0 equations. Yeah. So I believe the current at time 0 we got was 2. So 2 equals A1 plus A2. The reason why the exponents disappear is when you have an e to the power of 0, then you just get 1. So that gives us our first nice equation. Oh, plus 3.33, right? Because our total equation is a combination of the homogeneous equation and the forced response, right? So 3.33 plus this bit, this thing. So A1 e to the minus 35.85 t plus A2 e to the minus 0.35 t. Yep. Cool. So that gives us A1 plus A2 equals negative 1.33. Yep, negative 1.33. Okay. So that's one equation, right? That's one. We need to get the other. And the other we can get by, you usually have to use some of the equations here that you derived. I'm actually going to use, let's see. I think I'm just going to use equation 1. So I'll copy this and show you guys. So, okay. So, and I'm going to delete this. There we go. Okay. Keeping in mind that, again, the VC is 12 IR. So C 12C DIR on DT plus IR. Okay. And the current to the inductor, if you remember, was also 2. Because it's the same as the current to the resistor. Right, if I scroll back up to the initial circuit, the current through the 12 ohm resistor is the same as the current through the inductor, because the capacitor is open circuit. I'm probably not going to do the maths on this one just because it'll take me a while. But essentially what you do is you've got an expression for IR, right? You've got this. So you need to differentiate it and then add it again and sub in t equals 0, right? Because we're subbing in t equals 0 to this equation. And you'll essentially get just another equation in terms of A1 and A2. And if you solve simultaneously, it should give you, so my answers have 0.0 0.013, and A2 is minus 1.35. And that's it. You're finished. So all you had, so from then on, you just solve simultaneously using whatever method you learned, and then your final answer is 3.33 plus 0.013 e to the minus 35 point, whatever it was. I think it was 5. Yeah, 85. Plus, minus 1.35 e to the minus 0.35. Yeah, or 349 technically, but it doesn't matter. Amps, and that's it. Someone has a question. Are there any common trends in these sort of questions with the more complex circuits that have difficulty in deriving the initial second order differential equation? Like, it's not like every question is exactly the same, which is why I guess these, which is why I guess I prefer the Laplace transform method. But I've kind of made a point to write these steps in green because these are the steps that don't change no matter what. Like the way that you do them does change, but in principle, these will always be the same. So you find your initial values, you consider t greater than 0, you solve, and now, or I guess this is the part you were asking before with like, how do you derive the differential equation? It's essentially just doing either nodal and then, or just using the capacitor / inductor equation. It's sometimes hard to get a feeling or an intuition for it, but I think with practice you do get quite a bit better in, you know, identifying what you need to sub in. Like, it's like, okay, what do I need this equation to be in terms of? We need this to be in terms of IR. Are there any expressions of IR I can obtain? Yes, I can. So the voltage through the capacitor is the same as 12 IR. And you'll notice that I'm doing voltage through the I'm using the voltage through the inductor equation and also the current through the capacitor equation. Stuff that involves those is usually like a giveaway of what types of equations you should be looking for. And that all just gives you a way to get everything in terms of IR. Yeah, no worries. And then, yeah, after that, you get your characteristic equation. You find out whether it's underdamped or overdamped. You find the force response, solve for A1 and A2 using initial values. Now, so always you'll be able to get one of your equation by just subbing in t equals 0 to the current equation, this one, right? The other equation you can just get by using any of your t greater than 0 equation, as long as you're either looking at the current through an inductor or the voltage through a capacitor. In this case, IR for t less than 0 is the same as the current to the inductor, so that's fine. You can't do this with, like, let's say the voltage through an inductor. You can't do that. And that just goes back to the fact that inductors conserve current, and likewise capacitors conserve voltage. That's all. So yeah, you do get a bit of a feel for it after a while. I do recommend doing this past paper because the questions there are quite brutal. Some of the early ones. Did anyone have any other questions with regards to just this particular question? Because I know this was a bit lengthy, right? It's 13 marks. It's quite a huge question. Nope. All right, all good then. Okay, now I reckon I'm going to. Oh, by the way, if you have any questions in particular you wanted me to cover, I've got some power triangle stuff, Fourier transform stuff, Laplace transform. I was actually thinking of doing a similar question to this, but with the Laplace transform method. I think that would be really nice to show you guys, you know, what the difference is between these, and then you guys can kind of make your opinion on which one you prefer. But I do recommend knowing both. Knowing both is very good. Okay, so this one is simple. I think I'm going to do the simple one, just because it's shorter. I'll just scroll all the way down. paste. Okay, so this one is from 2018. I've tried to make most of the questions here recent. Like there's some ones from 2021 and 2019 in there. But yeah, so this one's from 2018. It's just, again, an RLC circuit. You've got another switch that opens at t equals 0. And then these two questions are basically just use Laplace transforms to find an expression for the current I of t, which is the current through the inductor. Okay. So we're going to do something different now. We're going to consider the Laplace transforms. Now, Julian Epps hasn't gone over, as far as I know, he hasn't gone over how to take into account initial conditions, but you do most certainly need to take them into account when you do the Laplace transform. In fact, that's the reason why we use the Laplace transform and not the Fourier transform. So again, I'm just going to solve initial conditions. So initial conditions. Oh. Give my laptop a sec. So what, the switch will be closed and you'll just end up having the 5 ohm. It's just a 10 volt source and then a 5 ohm. 5 ohm. And this is 10 volts. Okay. This is a really simple circuit. In fact, the voltage through the capacitor will just be 10 volts, and the current to the inductor is just going to be 10 divided by 5, 2 amps again. Okay, great. So yeah, this one is a bit nicer in the sense that it's a lot less effort. Okay, once we find the initial conditions, we're ready to consider the t greater than 0, right? So for this, we're going to actually, I'm going to go back to my solutions and show you guys what happens, because I've written over here what happens when you transform things from the time domain to the Laplace domain. So when you've got an inductor with a current running through it and a voltage through the inductor, as in this is the polarity of the inductor, right? When you transform that into the Laplace domain, you end up with SL, which is essentially just like j omega L, right? Except that j omega is replaced with an S, right? And you end up with this weird, it's like a voltage source, right? Which is in series with it. You can also add a current source in parallel, but I didn't bother memorizing that one. Both of them give you the same thing. So it's either you add a voltage source in series or a current source in parallel. I recommend just sticking with memorizing one, or since it's open book, you can, I'm pretty sure the equation is in the slides. If Julian doesn't have slides, it's definitely in the textbook. It's also on my formula sheet, which I will also share. But yeah, so the value of this this voltage source in series is going to be equal to L times the initial current. So as you can see that it depends on the initial current. That means that's how you're taking into account your initial conditions, essentially. That's all. And similarly with a capacitor, if this is the voltage through the capacitor and this is the current through it, when you there's an F there, but it really should be an L. So when you Laplace transform, you end up with 1 on SC, just like you've got 1 on j omega C, and you end up with yet again another voltage source. Pay attention to the polarity of it, because it is flipped, and I know that's a bit confusing. Just refer to the textbook, and just practice will make sure that you kind of remember these off by heart. But yeah, anyways, the value of this is going to be the initial voltage through the capacitor over S, where S is like it's like a variable, right? It's like a Laplace domain variable, frequency variable. Cool. So now that that's kind of established, what I've done, right? I'm actually going to step through it in this way because the circuit here is a lot neater. So we've got this circuit, right? In t greater than 0. We're going to add all of these voltage sources, right? And I'm going to do mesh, assuming my current is going clockwise, just because I arbitrarily chose so. You can also do it the other way if you want. It won't matter. The reason why I chose going clockwise is because it wanted I of t this way. So I just think it's more helpful to take it the same way as the answer took it. This thing won't load. I'll stop sharing for a second so that I know what's going on. I'll just give it a sec. Okay, there we go. I'll share again.
In the meantime, is there any questions?
Yep. Yeah, I'm not sure why that was. Anyways, okay, so just like there's a Fourier table for the pairs, there's also a Laplace domain table. It's mostly the same. Oh, Vincent's got a question. Why do we have 10 on S if there is no unit step function in the internal circuit? That probably comes around from that's a good question. It's was closed for a long time.
Is the 10 on S to do with the capacitor?
No, it's with the voltage source because that goes into 10 on S. That's a good question because
Yeah. I think we do just assume that there's
yeah, I think that's actually really annoying that it doesn't do that. But I think it's very common with questions to have the UT attached to them. And yeah, I think just assume that this is 0 for, well, but then this doesn't work, right? Because the initial conditions, I just had it as a 10-volt source. That's really weird.
I think this once we start doing the analysis.
Yeah. Sorry if I don't have a better answer than that. But usually there'll be step functions and not this circuit. Anyways. So yeah. I think just assume that U of t is there. You won't, I think nowadays the questions are a lot more fleshed out, so you won't get something like this in the exam. But anyways, just pretend it's a step function. Or just pretend that in the when we start analyzing it, then a constant value just Laplace transforms into a 10 on S. So it's a 10 on S voltage source. You've got the inductor, which is just LS, and then you've got a voltage source in series, which is equal to, the value of it is equal to L times I naught, right? L times I naught. And I naught was 2, and the inductance is a half. So it's just 1. Then we've got 20 on S. If you do 1 on SC, I think C was a 20th, was like 0.05 or something. So 20 on S. And then you see the voltage, the voltage source has the opposite polarity because it is that way on the diagram. So do pay attention because it can catch you off and lead to really annoying mistakes. And so the voltage across the capacitor was 10 volts we settled on, and it's just, so it'll be 10 on S. So essentially these two voltage sources are going to cancel each other out. And then you've got a 2 ohm resistor. Okay. Then then it's just like a mesh equation. It's essentially just one singular mesh equation, which you get minus 10 on S plus half S times I, minus 1 because you're going through the negative terminal, plus 20 on SI, plus 10 on s, so those two will cancel, plus 2i equals 0. That's your mesh equation, right? So now you've got an equation which is just in terms of I. So you don't have to do any, deriving of the differential equation where you had to get everything in terms of I. It just comes out. If you group your like terms and just separate the one out the other side, you get I times a half s plus 20 on s plus 2 is equal to 1. Which if you do some rearranging, you eventually get this. And as in the fraction at the bottom of the page. And most of these will involve you doing some sort of either partial fractions, or you can just go straight to the Laplace transform table. The Laplace transform table, I think, is not given to you in online exams. So it would be handy if you just had it on standby. You can just go to the textbook. Again, it's on ELSOC. The actual ELEC2134 textbook is on the ELSOC drive. So, and that will have both the Fourier and the Laplace table. In this case, it would be helpful if I had the actual table, because then can you pull it up just so I can say what identity Laplace.
Oh, sorry.
Oh yeah, do the Laplace one. Yeah. So in this case, I've got like a 2s on the top and a quadratic on the bottom. So, oh yeah, I think that should be good enough. Yeah. I just click on the image. Yeah. I think I'm using the which one am I using? Oh yeah. So yep. E to the minus at cos omega t. Oh no, I'm using this one. Yeah. That Laplace transforms to s plus a over s plus a whole squared plus yes, yeah, omega squared. Yep. And I'll also do the sine. I'll write the sine one. Sine omega t Fourier transforms. Most of these, it's very common for you guys to get sines. Omega over s plus a whole squared plus omega squared. Okay, so I'm just using these. You can find them even if you like Google Laplace transform table, just like I did, or once again they're on the textbook. So essentially, I'm gonna do a little trick, which is to I'm going to complete the square on the bottom side, right? So s squared plus 4s plus 4 gives me s plus 2 whole squared. And then I have to subtract 4. So that's why you've got 40 minus 4, which is 36. And then on the top, what I'm going to do is because if you look at the identity, the cos one, right, it's got s plus a on the top. So I'm just going to factor out the 2 because it's just a factor. So I'm going to take it out the front, and then I'm going to do I'm going to add 2 and subtract 2, right? So I've got s plus 2 here. And then, well, I'm actually adding 4 and subtracting 4 just because of the 2 factor there. So I'm adding 4 and subtracting 4. So I've got 2 times s plus 2 divided by s plus 2 whole squared plus 36. Someone has a question. Hi, I can't attend right now. Where will we find the recording for it afterward? It will be on YouTube. Yep. Anyway, so yeah, I've got this, and then minus 4 over, well, the same denominator. It doesn't change. So all I've done is I've just added 4, subtracted 4, so I get this. The reason why I've done that is because now the left-hand term is exactly what I want to be able to transform from a cos to the from the Laplace equation to the cosine with the exponential. All that is different is that it's got a factor of 2 out the front. So that's why I've got a 2 outside, e to the minus 2t, right? Because if we're going off of s plus a, where a is the power of the exponent, So 2e to the minus 2t. And then cos of 6t, since the square root of 36 is 6. If we're going off of this equation again, which is omega squared, and we've got 36 here, so 6. Then I've got minus, and then 4/6, because if we look at the sine one, at the sine equation, right, we have to have omega at the top, and omega is pretty much determined by the bottom, right? Where we've got s plus 2 whole squared plus 36. So our omega is like 6, right? So we need a 6 out the front. So if you just factor out 4 and 6, then it'll give you, so 4 and 6, and then it'll give you 6 over whatever was on the bottom, s plus 2 whole squared plus 36. So that's why I factored out 4 and 6 there. So then again, I get e to the minus 2t sine of 6t. And don't forget the u of t's, because that's how the Laplace transform works. You don't like they're absolutely necessary, because the Laplace transform only works for t greater than 0. So don't forget the u of t's. And that's your final answer, right? Yeah, all I've done in the last step is just go from 4/6 to 2/3. But yeah, so that was relatively simple. It was easier than the last question just because the circuit was easier. But I hope this showed you how to kind of take care of initial conditions with the Laplace transform. All you have to do is just add voltage sources in series. That's all. And remember what the value of those should be. That's pretty much the only difference. Did anyone have any questions about that question? Or if not, I think I'll go to a power question. Because there are like power questions which they're like asking every single time. They show up in every past paper that I know of. So I think it's very helpful. Okay, if no one had any questions, give me a second, I'll load the next question up. The question I had in mind was one where they've got like a voltage source and then they've got like a load, but they don't tell you what the load is. They just tell you whether it's like leading or lagging. And then they ask you to do a power factor correction, usually to unity. And then I just wanted to explain the maths behind it. But yeah, those types of questions I think get asked almost every year. I think it was asked when I took this course last term. So it's very helpful to know. So when you do the past papers, you'll come across so many of those, and they'll have answers as well, some of the recent ones. So if you can't get it from this workshop, practice will do you good. Yeah, all right. I'll just wait for my OneNote to. Not sure if you know this, but do you have any idea of a general average for the exam between all the offerings? Do you mean
really common?
Yeah, what do you
Like
mean
the
by
average grade that people get,
but what do you mean by offerings?
like term 1 and term 2?
Oh, right. I mean, I don't know for certain, but I've been told that it's usually like a 60 average. Would that be fair?
I don't think we
Yeah, I actually kind of agree. Yeah,
do that.
yeah, just do your best. Like, yeah, that's all I can really say. Don't be too stressed by the final. As long as you like do your study for it. They tend to be more lenient in the finals than they do in the midterm. Actually, I don't want to say that as well.
We can't really have any problem.
Based on experience. Again, I don't know. Like, I can't really comment about this final. I don't have any part in writing it or anything. But it's also just by this time that you guys have like gotten used to the course a little bit. So you guys are stronger electrical engineers, right? So you'll be able to solve the questions that maybe you couldn't in the midterm. So yeah, anyways, just do your best. Okay. After the power factor question, I will probably might do a Fourier transform one. Fourier transform properties. Those are always good to know. Okay. Paste. I'm going to share my screen. Share. Okay, back to questions. So you've got a circuit, and this one's actually a more difficult question. The reason I picked this one is because it's a bit unconventional. So hopefully if I cover this, then that should set you up for all the rest. Because usually they just have one singular of these like loads connected, but this time they've got two in parallel. So you've got a second figure one. You've got a 200-volt voltage source. You've got two loads. One of them is 30 kilowatts. The power factor is 0.55, lagging. It's important to specify whether it's leading or lagging, because just the value doesn't tell you whether the angle is negative or positive. Since cost of a positive thing is the same as cost of the negative. And then you've got a 40 kilovolt amps with a power factor of 0.65, also lagging. So the first question goes, sketch a power triangle for the source, clearly labeling and showing values for the real, average, reactive, and apparent power and any relevant angles. So essentially what we're going to do is we're going to combine these two loads, and because they're in parallel, we can actually just add up the reactive power and the average power and then construct a triangle based on that, just because they're in parallel. So yeah, true, because I don't know what you would do in series. Yeah, but they won't do that. Hopefully not. So yeah, these are in parallel. I'm just going to draw the power triangle for both of them. Yeah, so right, so this one, the first one, left-hand side, is 30 kilowatts, which, if you remember, kilowatts is or just watts is the unit for average power. So when I draw the triangle, I'm going to put 30 kilowatts here, right? And the angle, right, is cos inverse of 55. Oh, sorry, 0.55, right? Making sure I'm in degrees. So 56 let's say 6 degrees, if you inverse cosine that. Okay, that gives you enough information to calculate the average power. So sorry, not average power, the reactive power, right? If you just do basic trig, right? If you use tangent, right? If you use the tan function, you can find Q, which will be 30,000 times tan 56.6. So 30,000 tan 56.6, which is like about 45,500, just gone around. And the units for reactive power is VAR. And yep, okay, I'm going to put watts here as well. Cool, that's the power triangle for the first load. The second load is 40 kilovolt amps, which is the unit for apparent power, right? S. So instead of drawing the average power, I'm going to label the apparent power, which is 40,000 volt amps, with a power factor of 0.65. So if I do cos inverse of 0.65, I get 49.5. Hope everyone's following me. So all I've done is I'm just drawing the two power triangles for the load separately, and then I'm going to combine them. So this also it just gives you enough information to calculate P and Q. So P would be if you just use the cosine function, right? So cos 49.5 is P over 40,000. So P is 40,000 cos 49.5, which is about 26,000 watts. Yeah, 26,000 watts. And similarly, if you use a sine, it's going to be 40,000 sine 49.5. 40,000 sine 49.5, which is, or you can just use Pythagoras, whatever you want. It's like 30,000, 30, 416. VAR. Okay. So now that you have these two power triangles, since average power and reactive power are separate, you can just add them separately. So 30,000 plus 26,000 gives you 56,000 watts. And then you've got 30,416 plus 45,500, which is 75,916. Cool. VAR. It asks for all the values, so just gonna label the apparent power, which is the the magnitude of S, which you can just get by doing Pythagoras theorem on the triangle. So that just gives me 70. Oh, oops, not 70. Gives me 94335 or 336 volt amps. And the angle, once again, just use trig. There we go. So it's about 53.6. Great. That's it. That's the extent of question 1. So usually they won't have these two loads. This was just like a kind of an unconventional question, but I thought it was interesting. So that's question I done. Find the value of the capacitance C that when connected in parallel with the load will produce an overall power factor of 0.8. Okay, so it's not power factor correction. It's just adding a capacitor to make the power factor 0.8. And I'm just gonna say this should be 0.8 lagging. It didn't specify it really should, but just assume that it's lagging. So again, with the power factor correction questions, I think it helps if you draw the new power triangle. So if you 0.8, if you do cos inverse of 0.8, right, you get 36.9 approximately. You're assuming that the average power doesn't change since you're adding a capacitor, which is purely it only consumes reactive power, right? And then the final Q, right? You can just get by doing trig again, which should give you 56,000 times tan 36.9, which is about, I'm just going to say it's 42,000. It's like 42,045, but doesn't matter. Cool. Oops. VAR. So from here, you can calculate the change in reactive power, which is what you end up with minus what you started with. So you've actually gone down 33,000 reactive volt amps, or volt amp reactive. And that's all due to the capacitor, right? So the next equation I've just kind of memorized. I think it just comes from the power that a capacitor creates, right? V squared on R. So it's like VRMS magnitude whole squared over X, where X is the not susceptance, reactance of the capacitor, is equal to this. So basically just saying this capacitor is the reason for the change in Q being the reactive power in the circuit. I almost said quality factor. It's annoying that they're the same letter, but anyways, just rearranging for X, and VRMS is 200 on root 2, right? Because if we scroll up, this is 200 volts, and it didn't specify whether it was RMS or not. So if it's not specified as RMS, then just assume that it's not. Otherwise, it will say. I've had questions in the past where it does specify that it's RMS, so do pay attention to that. So 200 on root 2 squared just gives me 200 squared on 2 times 33916. If you mash all those numbers on your calculator, that should give you 0.5896. It's about 0.59. So that being the reactance of the capacitor, and which is 1 on omega c, right? So, right, because the impedance of a capacitor depends on, or I should say the reactance, it depends on omega and the capacitor value. So, well, we want C, right? We don't know what it is, and we know the angular frequency because we know the frequency is 50 hertz. And converting between the two is just a linear conversion. So C equals 1 on omega, which is 2 pi times the frequency, times 0.59, which is 2 pi times 50 times 0.59. You get about like 5.4 millifarads. So 5.4 millifarads. Cool. That's it, right? That's your question 2. So all we've done is we calculated the final power triangle after the correction. We said, all right, what is the difference between what we started with and what we ended up with? And it was this. Then we equate that to the power that is the reactive power that the capacitor cancels out, right? And we use that to solve for the reactance and hence the capacitance value. That's all. So question 3, determine, this question was a bit weird. Took me a little bit of time to figure out what it was saying. But so with the capacitors of C from part 2 still connected in parallel with the load, so like that, determine the phase angle between the capacitor current, so this current, and the source current, which is this. Okay. So for triple I, I'm gonna start by, so this is the final power triangle, right after the power factor correction. Someone's got a question. When would you add an inductor to correct the power factor? That's a good question. I probably should have specified. So a capacitor, okay, this is what the triangle was before. This is what it was after. When you want to reduce the reactive power, or as in create like negative reactive power, then you add a capacitor. If you want to add, then you add an inductor. So just because we went from a value of 75 kilovolt amps reactive to 42,000, right? We went down, so that's a capacitor. If we were going up, then we would use an inductor. That's the only difference. So literally the same process would be exactly the same, except for you, instead of the susceptance of a capacitor, you'd use omega L, right? Which is the, sorry, susceptance, I meant reactance. You'd use the reactance of a inductor. Yeah. Would inductor be in series in parallel? It's also in parallel, right? Because the whole principle of the power factor correction is that we don't you do it in parallel. So it just yeah, the whole principle that we work with is we just attach it in parallel, and that allows us to just straight up minus the powers, the reactive powers. You guys aren't, I don't think you guys are taught what to do in series. So it's all in parallel. The method is always just attach something in parallel. And that's actually what indicative of what we do in real life as well. So both, and I'm sure Julian has already mentioned it, but usually you get a capacitor. So your load is usually inductive, which means you want a capacitance to cancel that out. Yep, no worries. Okay. So anyways, back to question 3. So question 3 was just asking us to find the difference. It's like the phase angle between the capacitor current and the source current. So it's like the difference. So let's just worry about the source current angle first, right? So this is the power triangle after the power factor correction, right? You've got, so the angle, this angle tells you the angle of the source, right? So, oh, sorry, no, it tells you theta, right? Where theta is theta v minus theta I, right? And well, you know that the voltage, it didn't specify that the voltage source had any phase or anything. So it's just going to be, well, so theta v is going to be 0, right? Because it just says 200 with the frequency of 50 hertz. So 0. And the theta is like, what was it? It was like 36.87 or something. Minus theta I. So theta I is equal to minus 36.87. Cool. Then we can use the fact that the capacitor current will be 90 degrees out of phase, because I believe this is ELEC Quad 1 knowledge. But if you just use the reasoning that the source current, the capacitor will just be 90 degrees out of phase with that, then you should get the difference as being minus 36.87 minus 90 degrees, which is like about 126.87. That doesn't matter if you leave the minus sign or not. If you're still not satisfied with that, you can also just calculate the capacitor current by just going, IC is V over the impedance of the capacitor. So when the voltage, when we're doing power factor correction, we're assuming the voltage doesn't change, as in it stays at 200. So 200 over like 1 on J omega, which is 2 times 50. Yeah, that's right, Vincent. Yeah, it's 90 degrees out of phase with the source voltage. That's right. Yeah. No, sorry. No, it would be 90 degrees out of phase with the source current, right? Because the current is this, and then it's 90 degrees out of phase with that. Yeah. So if you calculate the current going through the capacitor, right, we got 5.4 millifarads. You'll find that this gives you about like 339. We don't really care about the number, but we care about the phase of 90. So, so 90. So yeah, I mean, you can do like 90 minus 36.87, which will give you, it doesn't matter. But just as long as the magnitude of the phase difference is correct. But yeah, those are like just two ways. Since it's asking for the phase difference between source current and, right, so isn't that just the answer, 90? Since it's asking for the phase difference between source current and capacitor current. Actually, that's a good point. Let me have a think. Well, yeah, but maybe you're right then, that it is the voltage. What did it say? The capacitor current and the source current. Yeah, I would think it would be. When I looked at the solution, it had 126.87. So I was going off of their answer. Peter, do you have any input?
Is it? Which currents?
Oh, it's just, so you've got a source current and then the capacitor current in parallel, and it's asking to determine the the phase angle between the capacitor current and the source current.
Yeah, that's fine. You have differences in phase between currents. The only
Yeah, but it won't.
requirement is that the voltage and the current be 90 degrees out of phase.
Yeah, so wouldn't it be 90 and not 126 point? Well,
No, because you're looking
source current. Source current. Yeah, right. It's not the
source current is different to the capacitor current.
yeah.
Supply more.
Yeah. Yeah. Well, yeah. I mean, I got the source current from the power triangle, right? Where theta, the power triangle gets you theta, right? Which is theta V minus theta I. And then since it didn't specify phase for the voltage source, and the phase would be 0, or for the voltage, like theta V would be 0.
Yeah.
So then you've got like theta I is what was it? Yeah, theta I is minus 36.87. So that's a phase of the source current, right? And then the capacitor phase would be, I thought it would be like 90 out of phase with that. I think it's because theta I is the phase current with respect to the like source, and this, right? Now I think you're right, because this phase is the phase also with respect to the source. So if you take the difference, yeah, you should just get 90. In my eyes, it should be 90. I'm not sure why the answer. Sometimes the answers for these are a bit like muddled up. I think it should be 90. If it was the phase of the capacitor, then it would be this 126.87. That would be right. So I guess when I just did this, I must have interpreted it as not the phase difference, just the phase of the capacitor current. Okay. Yeah, because that makes more sense. Otherwise, it would be 90 degrees, because that's what we're taught, right? Capacitor is 90 degrees out of phase from the source, always. Yeah. So I think that's more correct. Yeah. Okay. Did anyone have any questions about that? So everything apart from that is still correct. So questions I and double I. Those are pretty like standard methods for calculating, power factor and power factor corrections. Those never change. As long as you follow these, then you should be fine. Just knowing when to add a capacitor and inductor in parallel. I also got 90, but you did it a bit differently. Okay, yeah. Then yeah, in my eyes, yeah, I think it should be 90, and not 126. 126 would be the actual angle of the capacitor current. Yeah, as far as I can tell. Cool. I'm probably going to do Fourier transform question next. Because I think everyone kind of gets freaked out with the different properties that you can have with the Fourier transforms, which is fair enough. There are a lot. I'm going to focus on duality because that's the one that boggles people's minds the most. Just out of curiosity, how did you do that question, Vincent? Not 100% sure it's correct. That's all right. But I solved for IRMS using Q equals IRMS. Yeah, that works. I think that works. Q equals. Right, where Q is the reactive power that the capacitor produced, right? Or the reactive power consumed, sorry, by the capacitor. Yeah, all right, then that also works. Yeah. You can also do the voltage. That also works. RMS voltage. And you got 90. Okay, yeah. Then I think I'm happy with that. Sometimes I just blindly follow the solutions. Okay, Fourier transforms. So this one is from the 2020 term 1 midterm. So it's pretty recent. Okay. So 2020 term 1. So, and it's got Dirac deltas, which is another thing that people kind of are like unsure about sometimes. So given that the Dirac delta function Fourier transforms to just 1, then use the duality property to derive the Fourier transform for f of t equals 1. Okay, so again, this one it's pretty weird, and a lot of the times it's kind of uncomfortable to use dualities because it's got like this weird implied symbol, and it's like, what do we do? But it's okay. I'm going to write the duality property. So the Fourier transform of a time varying signal, right, is its equivalent in the Fourier domain, which is what you guys have learned. This implies that this is also true. If you Fourier transform the same function, but sorry, hey, sorry, you probably want to move on, but I think the answer was right. Oh, okay. I'm open to. So what have you done? So you've got, I see. Yep. So you've calculated the current to the capacitor, which is right. And then source current is right. Yeah, you've done the same thing. Or you've done the same thing as me, but that's
So theta IC is always 90 degrees. The current through the capacitor always has a phase of 90 degrees. But here you've got also an additional term that's the
the input current.
I think all it's worried about is the
theta.
The actual. Yeah, it's a poorly phrased question, possibly.
Yeah, it depends. So
Worth getting a headache.
Yeah, probably not. Like, I mean, it's 2 marks.
Yeah. Just put everything down and then. Whatever.
It's 2 marks. You really like part of these exams is like you gotta recognize when a question is worth attempting and when it's not.
Yeah.
There's another question that I don't know if I'll have time to look over. It's another Fourier transform question, which is worth 3 marks. But I'm 100% certain that with reasonable certainty, I'm certain that it's wrong and it's worth 3 marks, and the working for it is absolutely insane. So I might look at it just because it talks about convolution, which is something that, again, is mentioned in the course, but not it's touched very lightly, and it can come up in the finals, right? Because it is a topic. Yeah, with regards to the current one, I'm not sure what happens. What happens in this case if the solutions are just wrong? Look, I don't want to say that the solutions are going, like the exam is going to be wrong. Just like your exam is made by competent people. They're not going to make mistakes. Especially like with the recent ones, like the ones that Julian has been taking, like you just don't worry about, wrong answers. Just do what you can. Do the questions. Yeah, for the case I was talking about, with that one, just don't worry about it. Like it's nearly impossible that something like that happens. Yeah, so just attempt what you can. If a question's not worth the headache, like it's a 3 mark question and you're spending a lot of time figuring it out, then just skip on to the next question. Usually those ones will be ones that don't have any like error. They don't have any subsequent parts. So it's not like you'll have an error carrying forward and you won't be able to solve the rest. So, yeah, with regards to this one, I don't particularly know, but I'll move on to the next one. I'll try and think about it. And if I come up with a concrete answer, I'll let you know. Yeah. Okay. Because like in here, all we did was we calculated the phase of so we calculated the capacitor current that has a phase of 90 degrees with respect to the source voltage. We calculated the source current, which is some degrees out of phase with the source voltage. Then we did the difference and we got 126. I actually think that's the correct interpretation of what we did. So the source current, I think it's what you were saying before, Vincent, where the source current is actually 90 degrees out of phase with the source voltage. That makes the most sense to me. I think if you look at the previous slides, you'll find that it would say the same thing, right? So it's 90 degrees out of phase with the source voltage, and the source current will also be some degrees out of phase. And then you're just doing 90 minus that.
Yeah,
that's
your
it.
0 point is your voltage.
Yeah, and that makes sense because like all of with the power correction stuff and all of that, you always get taught that voltage is like the reference. So that actually does make sense. I guess I think problem solved then. Sometimes, yeah. Making a fool out of myself a little bit, but that's okay.
So easy to get mixed up.
Yeah. Well, as long as we're having a healthy discussion about it, then.
Yeah.
Okay. So you've got a function in t, you Fourier transform it, you end up with a function in frequency called capital F of omega, right? This implies that if you've got capital F of t, that is, you've got the Fourier domain signal, and you just replace the omega with a t, so you end up with something that with respect to time. If you Fourier transform that into the frequency domain, all you get is the original lowercase f of minus omega with a factor of 2 pi out the front. A little bit confusing there, but I think it's more helpful to think of it from like a mathematical perspective, you know? So if you get this Fourier transform function, you substitute t instead of omega, you Fourier transform that, you end up with 2 pi, and then the original time varying signal, but substitute minus omega where every t is. That's it. That's all duality. Entails. Right. Okay. So using the duality property, derive the Fourier for f of t equals 1. So once is to derive what the Fourier transform for just 1 is. So it would look like this, as in that's the time varying signal. Okay, so I'm gonna sub in the Dirac delta function now, as in, so 1, 2. 1 implies 2. So here's 1. The Fourier transform of the Dirac delta function equals f of omega, capital F of omega, which is 1. That was given to us, yeah. Because it told us that the Dirac delta transformed into just 1. So this implies 2, which is the Fourier transform of, now we get the capital F of omega, which in this case is 1. And then we substitute t where there's an omega. But in this case, there is no t. It's just a number. So it's just going to be 1. And I think you can see where this is going, because now we're going to be solving the Fourier transform of 1, which is what the question was asking for. So then the Fourier transform of 1 is equal to 2 pi and then the original time varying signal, which was delta, Dirac delta of t, but then substitute minus omega. And that's it. I'm just gonna say this. So this answer is fine. This answer is also fine. 2 pi Dirac of omega. Because I went down a bit of a rabbit hole on Dirac deltas the other day, and so one of the properties of the Dirac delta is like Dirac of x is equal to Dirac of minus x, and that should kind of make sense because the Dirac delta is just like a spike, so obviously it's even. So Dirac delta function is even. So either of these answers is completely fine. Cool. So we've just verified that the Fourier transform of the time varying signal 1, f of t equals 1, gives us 2 pi lambda. Hey, Riley. So 2 pi Dirac delta of minus omega. Don't know why I said lambda. Okay. Now for the second question, which is a bit more interesting. And this is one that I think is personally a little bit difficult, but it's a nice question. So using the result in part I and the frequency shifting property that says if you frequency shift in the time domain, that if you frequency shift in the Fourier domain, that corresponds to a phase change in the time domain. So Fourier domain frequency shift is the same as time domain phase shift. So we want to derive the Fourier transform for f of t is cos omega naught t. Now, you do get given what this is. Like, you know that it's going to be a mixture of Dirac deltas, but it wants you to prove it from first principles, which is a little bit difficult. But I hope once I go through it, you'll be able to see that it's just like all of these types of questions are like kind of like maths based. It's a lot of like being good with sort of algebra. So most of you will be doing maths right now anyway. So hopefully you guys are kind of in the right mindset. Okay, so we're gonna start with, so f of t is cos omega t. We want the Fourier transform of this. We already know that, well, if you look at the table, it's going to be a mixture of Dirac delta functions. So it says, using the result in part I and the frequency shifting property. Now, the frequency shifting property, you see how it's got like this e to the j omega naught t. That kind of clues me in that I want to I want to write this cosine in terms of exponentials, right? See, because cosines in science can be written as exponentials. That's kind of like my first clue. So if I rewrite cosine as a combination of exponentials, I get this. So what is it? E to the minus j omega t plus e to the j omega t, and I think over 2. Yeah, I'm just going to take a half out the front, because with Fourier transforms you can just take out constants because they're linear transformations for all you maths 1b or math 1a people. So you've got a half times the Fourier transform of this thing, which I'm actually going to write as, keeping with the linearity property, like the linear transformation. You can actually Fourier transform the individual bits as well, as in just the individual terms, like that, right? Okay, and I'm going to do something a little bit weird. I'm just going to write this as 1 times e to the minus j omega t. And similarly, I'm going to write this as 1 times. So the reason why I'm doing that is because I'm going to use the frequency shifting property that it told us, because we know what one Fourier transforms to, right? We calculated it in part I, transforms to this, right? We know that if we add a phase in a time domain, that corresponds to a frequency shift in the frequency domain, right? Because that's what the question told us, right? Over here, phase shift in time domain, frequency shift in frequency domain. So I'm going to write this as a half. Actually, I'm just going to take a half out the front, right? So one Fourier transforms to 2 pi Dirac of minus omega, right? But then we're going to shift it, in this case, by minus omega. And 2 pi, and same with this one, minus omega plus. Oh, oops, other way around, but it doesn't matter. This should be plus, this should be minus. Yep. There we go. So all we've done is recognize that a phase shift is a frequency shift in the Fourier domain. Phase shift in time domain is frequency shift in Fourier domain. So all that's left is to kind of neaten this up a bit. So we've got a half of the outside of, oh, actually the 2 pi's are going to cancel it out. So I'm just going to write pi out the front. So we've got Dirac of minus omega minus, sorry, plus, yeah, no, sorry, that was right the first time, minus omega naught, plus Dirac of minus omega plus omega naught. And again, if you use the property that Dirac deltas are even functions, and you get omega plus omega naught plus Dirac of omega minus omega naught. There you go. That's it. And that's actually the exact Fourier transform of cosine. You can verify it on the table if you want. So it's just a bit of algebra to get us to the point where we can kind of manipulate the properties, the Fourier properties, to get us something nice. I hope you guys were able to follow that. It might have been a bit too maths heavy, but yeah. Let's see what I want to cover next. I don't have too many more questions. What else? I think there was some resonance stuff that I wanted to go through. Feel free to ask any questions that you guys have while I get the next question up. Oh, I might do a mag circuit, magnetically coupled circuit. Yeah. Oh, actually, do I want to do that? Does everyone want to do it? What would people prefer? Would you guys prefer a resonance question or a magnetically coupled circuit question? Whichever one is harder. Resonance. I think it's a bit arbitrary, whichever one is harder. The magnetically coupled circuit I have is actually quite an easy one. But then so is the resonance one. I think I'm going to go over the resonance. Resonance, if there's a quality factor. There is. So I think I'll go through the resonance one. But yeah, like with the magnetically coupled circuits, typically, and I'm not going to say that this is indicative of what you'll get, but typically in past exams, they usually like to give ones that are, like you won't get the ones that you've gotten in the labs, for example, where it's like, you have like multiple mutual inductances to take care of, and it's like a whole thing. They usually, like in the past exams, they keep it like just 2 inductors, but you never know. Okay. Share screen. Okay. So Figure 5 shows an RLC resonance circuit. The circuit is designed for a resonance frequency of 1000 Hz and a quality factor of 200. An inductor L of value 0.02 Henry is selected. The resistor R in the circuit is simply the internal resistance of the selected inductor. What value of the capacitor C should be selected? There's probably a few ways you could do this, and keep in mind, it's 1 mark question. I think you can just use the resonance condition, if I'm not mistaken, which is the same for series and parallel RLC circuits. So 1 on j omega c is j omega L, I believe, is the equation, which is essentially the reactance of the capacitor is the same as the, is that like the negative of the reactance of the inductor. Yeah. I'm going to cancel out the, I'm just going to cancel out the i's, equals j omega L. Sorry, get out the omega. So C is 1 on omega squared L. Yep, 1 on omega squared L. Which you should get is equal to, what was omega? It said resonant frequency of 1000 hertz. So 2 pi times 1000. Got to be careful not to accidentally use hertz instead of rad per second, because omega is in rad per second. And the inductance was like what, 0.02, I think. Yep, 0.02. So that gives you 1 on 2 pi times 1000 whole squared times 0.02. So that gives you a value of 1.27 microfarads. There you go. Okay, the second question goes, what is the value of R? Good question. So with this, Alex, you can use the resonance equation. I always forget them. So it's you just use the series one, which is 1 on, so quality factor is 1 on omega naught RC. But I always tend to forget them. The one with the parallel network, I think, is it's something with L on R and omega naught. Or it's like, yeah, something like that. We can just quote these directly. Yes, of course you can. So I mean, that would be in the lecture notes. If I go to the like resonance, you can pretty much, yeah, see. So this is the series RLC circuits. And also keep in mind the I don't know, you know, that's right. And then what's the parallel one? Yeah, parallel resonance. There we go. It's R on omega naught L. Do you know where they come from? Julian didn't really explain it. The quality factor. Well, it says here by definition, this is it. So it's just defined as that. It just so happens that we define it in a way such that it gives us the selectivity of the circuit. The maths there is not really explained.
It does also come out when you if you have a two-pole sort of equation on your denominator, then you can derive them that way. So you probably will see them later on in electronics and those sorts of things.
Okay. Yeah. And two-pole arising from the fact that you've got a capacitor and inductor.
Exactly right.
That's where they come from. Okay. Right. Yeah. So that's just out of interest. Okay. So Q equals omega. 1 on omega naught RC. So, and then you can just rearrange for R if you just do this. So subbing in all the values I have for omega naught, which is 2 pi times 1000, Q, which was, I think it was 200 in the question, and C, which was 1.27 microfarads, which we got in part I. So you get 0.628 ohms. Question 3. What should the voltage rating VC be of the selected capacitor? So essentially, it's asking what is the voltage running through the capacitor, because that's the voltage rating that it needs to have. This one's a pretty simple one. I don't know if you guys remember, but there is another equation in the slides which essentially says that the capacitor voltage is equal to Q times the source voltage. It's not a very well-known one, but you can just quote it. Like I said, it's open book, so you can have equations with you on the day. So VC is Q times VS, where Q is the quality factor of 200, and VS was 10. You can also just work it out by, just analyzing the circuit, right? Because you have the resistor, you have the capacitor, and you have the inductor, right? So you can just, voltage divide. But you can also use this equation. That also works. So 2 kilovolt rating for the capacitor. Okay. I think now we'll probably have time for the magnetically coupled circuit question. There we go. Mag circuits. But yeah, this is just one random one I found. What year was it? 2020 T3. So fairly recent year. Yeah, there we go. Okay, in the magnetically coupled circuit of figure 2, find the RMS voltage across the 3 ohm resistor. Just keep in mind that the voltage is in RMS already. So you actually don't have to do any RMS calculations because everything is in RMS since the source is. Oh, and so both sources are, I mean. Otherwise you'd have to convert. Okay. For most of these ones, it's really helpful to do mesh. Like I think mesh is just way more helpful. I don't think I've ever done one of these questions without mesh. That wasn't like a transformer question. So I'm going to redraw the circuit. What was this? 1 ohm. This is J5 ohms. The dots there. Everyone kind of has different methods for taking care of the dot terminals. I think both methods were covered where, the just doing it regularly versus doing the dependent source method. I actually never learned the dependent source method. It's honestly like fine if you use either. It's just that if you use the dependent source method, it can be a bit easier for the marker to follow your working. So that's one advantage of it. So that's 5. This is minus J. And I don't know, I'm just gonna take 2 currents, I1 and I2. I don't need to do the third mesh because I'm just gonna end up with I3 is like if I do this, it's just 5. I3 is 5 with a phase of 0. That's all. Okay, so all right, well, I'll start with the first mesh. Mesh I1. So minus 20, the phase of 30, plus I1 times 1, plus 5J I1. Right, so that's, oh no, I've gone the other way around, haven't I? Sorry, plus 20J. Yeah, this should be plus 20J. So it doesn't matter what? It doesn't matter I'm taking the polarity as like this, but I tend to not label them and just always take them as positive when I'm going around a loop. And I find that saves me a whole lot of confusion in the future. However, the dot terminals do matter. So my current is going through here, right? So since it's going through the dot, it's entering the dotted terminal, right? Oh, and the mutual inductance, what was it? 2J. So since it's entering the positive terminal, right, I'm going to have plus 2J, and whatever is going through the dotted terminal of the other inductor. So in this case, it's negative I2, right? Since I2 is going here into the non-dotted, so whatever's going into the dotted would be the negative of whatever the I2 current is. So negative I2. If the dotted terminal was here in this case, then I would have put a minus there, since it's entering I want what enters the dotted terminal of the left-hand 5J inductor. That's how I work out the magnetically coupled circuits. Everyone's got different ways, but they're all the same in the end. Anyways. So that equals 0. So if I just group my like terms, I'm also going to use this opportunity to teach Cramer's rule to anyone that doesn't know it, because you do need to, or you don't need to know it, but it's helpful, very helpful. Okay. So that's one equation. I'm going to do the other mesh now. Mesh I2. So if I go around, I've got minus J I2. Well, actually, it should be minus J I2 minus I3, which is 5 with a phase of 0, plus 3 I2 plus 5J I2. And then I'm going to do so since the current is entering the negative or the non-dotted terminal of the inductor, then I'm going to put minus 2J, which is the mutual inductance, and then whatever's in this bracket is going to be whatever current enters the dotted terminal of the other inductor, the left-hand one this time. Which is I1, right? Since I1 is entering the dotted terminal, so I'm just going to write I1 inside the brackets here, I1. And the minus sign here came because the I2 was entering the non-dotted terminal. Cool. So once again, I'm just going to group my like terms. So minus J plus 5J, so 4J plus 3, and then on it should be minus 2J I1, and then there's just a 5J. There's just a 5J at the front, so equals negative 5J if I move that to the other side. Cool. So now I've got two equations. I like to write these as like a matrix. So 1 plus 5J minus 2J minus 20 with a phase of 30 degrees, and then minus 2J, 4J plus 3 minus 5J. So I've got my I1 column here, my I2 column here, and then my solution vector over here. Most of you guys will have had to have done maths by now, so you should be familiar with matrices. If you're not familiar with how to calculate the determinant of a matrix, that would probably be helpful to know, because Cramer's rule does depend on you knowing how to do determinants of 2 and 3 by 3 matrices. In this case, it's a 2 by 2, but sometimes in questions you might get a 3 by 3 matrix, in which case you'll have to know how to do it. I actually think I'll go through it anyways. I think it's good to know Kramer's rule is very useful. So let's say you want, so what did we want to find? We wanted this voltage, and so we were interested in I2, right? Because that's a current that goes through the resistor. So if I want to solve for I2, I'm going to do the determinant of this matrix where it's the same matrix, but you replace with the I2 column with the solution vector. Oh, oops. Yep. So I hope that makes sense. So all I've done is the same matrix, but I've replaced the second column, which is the I2 one, with this solution vector over the determinant of the original matrix with nothing done to it. So there we go. So with 2x2 matrices, A, B, C, D. So the determinant is just AD minus BC. That's it. For a 3x3 matrix, A, B, C, D, E, F, G, H, I. You can Google this, by the way, but I just want to go over it. It's A times the determinant of E, F, H, I. So A times the determinant of this matrix minus B times the determinant of this matrix D, F, G, I. So and then plus C times the determinant of this matrix D, E, G, H. You can Google these, so don't worry about memorizing it right now. But that's just how to do one for a 3x3 matrix. And of course, you will still need to calculate these determinants, which you can do by via this equation. So I'm going to do 1 plus 5j. There we go. I'm going to quickly put that into my calculator and hope I can do it fast enough and that I didn't make a mistake somewhere. Oh, okay, yeah. Okay, so I get 2.605 with a phase of minus 165.8 degrees. And this is for I2, keep in mind. I'm just going to check that that's right. Yeah, that's right. Okay. Last thing is it wanted the voltage, right? Where the voltage, it specified the polarity was this. And so I2 is actually going the other way around. This is negative I2. So all we need to do is E naught is negative 3 I2, which is, oh, oops, just negative 7.57. Oh no, forgot to convert that to polar form. It's 7.81 with a phase of, well, it's the same phase because you're just multiplying by a scalar, volts. Anyone have any questions with that? I guess the only tricky part is just knowing what to do with the dotted terminals. That's all. Topology. Okay, that sounds good. We're reaching around the 3 o'clock mark, which is when we said we'd wrap it up. However, I am open to staying a bit over time. There is one question here which I didn't want to go through just because it took a lot of working, but I think it's a nice enrichment question if you are interested. And I suggest you attempt it yourself. But if you want, I can go through it. It's a Fourier transform question and it involves convolution. Is that something you guys would be open to seeing?
For those who are heading off, thanks so much for joining us.
Yeah.
Yeah, we'll take another look at this question. Why not?
Yeah, for sure. Yeah, thanks everyone for joining. I didn't expect people to have such like open discussions about the questions. That was really good to see. And as always, good luck with your finals. I'm sure like everyone here, just do your best. Yeah, you'll do well. Don't worry about it. I think it's natural to panic over finals. I'm panicking myself. Not gonna lie, I have never seen convolution used. Thank you, Asan. You've never seen convolution used. Didn't it come in your midterm? Wasn't there an orthogonality question with it? Oh no, that was something different. Sorry, no. It can pop up. Like just because it hasn't shown up in past exams doesn't mean they're not going to do it this time. Yeah, didn't attempt it. Yeah, that question was sneaky because it was stolen from a final, and it was put in a midterm. See, that's an example of a question where I could reasonably see myself like attempting, maybe not getting, and then just skipping. Because it was only worth a couple of marks. Sure. Yeah. Yeah, I mean, and even aside from will this be in the exam or not, I know your mind's probably not on this, but just I think looking at convolution this early on is really helpful for just because you're going to be dealing with it a lot later on, particularly in DSB, I think, which I haven't done yet.
Yeah, you do get a bit of a taste of it, but the high yield stuff, I reckon. But yeah.
Yeah, pretty much. Okay, I'll step through this question since we're pretty much finished. But like this entire course, I haven't seen it. Really? When I did the course, we did look at a couple of questions that had convolution in them. I'm not sure whether it was in lecture or in like a workshop or something, but it did definitely pop up. And Julian would have mentioned it when he talked about it. I'm not sure if he touched it ever since. But yeah. So there's this one question. This is from 2019. There is no solution to this, as in the solution wasn't available. And I'm not gonna just say that it's wrong. But I have had a chat with a bit of like I have had a bit of a chat with some higher years, which seem to agree that this is very similar to what the final answer should be. So the question goes: prove that if a voltage waveform v of t equals cos of omega t is windowed by multiplying it in the time domain by this function, then the Fourier transform of the resultant signal xt is vt multiplied by wt is capital X of omega, that thing. That might look a bit daunting at first, but it's not actually too bad once you break it down, where it's just two exponentials and a sinc function. That's all. Now, you might notice at first that this function doesn't depend on omega, which is where I think it went wrong. You can see it's only got omega naught on there, which doesn't make sense. The only way that you can get a constant value in the Fourier transform is when you Fourier transform a Dirac delta, which is not what we're doing. We're Fourier transforming a cosine. So the actual answer that I have is very similar to this one, except instead of the omega naughts, it's got like omega plus omega naught or omega minus omega naught. That's all. That's So my answer is just a bit different, but I think it's right. I'm not saying this is the definite right answer, but the process is correct. Okay, so where do I start with this? So we want to prove that when you multiply these two functions in the time domain and you Fourier transform that, you end up with this. Well, okay, we're going to see what we end up with. So for this, we need to use a special property of convolution. I don't know if Julian has talked to you guys about this, but with convolution, a multiplication in the time domain is equal to convolving in the frequency domain, and vice versa. So that means a multiplication in the frequency domain corresponds to a convolution in the time domain. So that is to say, Vt times Wt, when you Fourier transform that, that is equivalent to convolving the Fourier transforms of Vt and Wt. So it's the Fourier transform of capital V of omega. Sorry, yeah, it's the Fourier transform of Vt convolved with the Fourier transform of omega of Wt. Yep, so that's what I was saying. Later, we will also use that convolving with a Dirac delta gives them. Okay, so we're going to use some nice properties of Dirac delta functions, which is mainly this. It's called a translation property. Like, this is just specific to this question. You don't really have to know this. Yeah, but so when you convolve with a Dirac delta shifted by, let's say, like T0, that equals to just time shifting the signal, and likewise with frequency. I can prove it if you want. It's actually a very short proof. It's just using convolution, which is, if you guys don't know the equation for convolution, so the definition, when you convolve two functions together, that's equivalent to integrating between the bounds of negative infinity to infinity. Your integral is with respect to another variable tau, where you've got f of tau, which is the same function but with tau subbed in instead of t, times g of t minus tau, where t is just like a constant, treated as a constant, right? Because we're integrating with respect to tau. That is what convolution is. I will share these solutions. Actually, do you know if there's a way that I can share them for people outside of this meeting?
We'll find a way.
We'll find a
Might
way.
be via email or
Yeah, maybe send out an email.
yeah.
Because I will.
Or we can throw them on the website somewhere.
Yeah. Is the convolution operator can be present on either side of the equation, right? So we can have xt convolved with wt to get xw. What do you mean? So either side of which equation? Well, yes, that's right. So essentially with this equation right here, you can move the convolution operator here and then just have this as a scalar multiplication, and that works. So multiplication in the time domain is convolution in the frequency, and vice versa. Multiplication in the frequency is convolution in the time domain. So yeah. Anyways, I probably won't step through the proof for the translation property, because it's I mean, you can have a look when I share this document. It's pretty simple. You also use another property called this sampling property, which is actually the one you learned in the course, where the Dirac delta samples a function at a point A. Yeah, so I won't step through that, but you can look at it if you want. So essentially, what we're going to use is, oh, come on. So f of t convolved with Dirac of t time shifted by t naught is equal to just the original function f, but time shifted is t naught. And the same thing applies with any function, right? Even a frequency function, right? It's not like this just depends on time, right? T is just like a variable, right? Can also be omega. So capital F of omega convolved with Dirac of omega shifted by a certain amount gives you this. It's just frequency shifting the original signal. So it might be a bit hard to follow, but bear with me. So what we're going to do is we're going to convolve the Fourier transforms of V and W because we wanted we wanted Vt times Wt is equal to capital V of omega convolved with capital W of omega. W is probably a bit confusing there because it's very similar to omega. That's the question's fault, not mine. All right, so capital V of omega is the same as Fourier transforming a cosine, right? Which, again, we did prove this today. It's just a mixture of Dirac deltas. This is the result that we got a while ago. Calculating the Fourier transform of the second signal, W, is actually not too complicated. Remember, it said that the function Wt was just like a step function. It's like it goes up and then down. Will my laptop let me draw it? Yes. Okay. So it just goes up and then down. You can write it as a mixture of step function, which I have written, but you can also just realize that it's just equivalent to Fourier transforming 1, because this is a height of 1. It's just Fourier transforming 1 within the bounds of alpha and beta, because everything else, the integral is going to give you 0, since it's defined as 0 for elsewhere. So it's just within the bounds of alpha and beta, you're integrating a constant value of 1. So that's what I've done here. And of course, the e to the minus j omega t is just a constant that you get from Fourier transforming. So a bit of algebra later, you just get this, right? J e to the minus j omega beta over omega minus j e to the minus j omega alpha over omega. Not the neatest expression, but it's still pretty nice. Here's where things get a little bit messy. What I've done there is a trick that you don't have to know, but I've factorized beta plus alpha onto so e to the minus j omega beta plus alpha over 2. And I've also factored j over omega. So I've taken this thing out the front. Then you've got these two exponents. You might be thinking, why on earth are we doing this? But it's actually just because when we do this, it actually this actually devolves into a sine function, because you've got these two phases are the they're the complete negatives of each other. And you know that when you have like e to the minus j omega plus e to the j omega, you get a sine. In fact, you get 2j times sine of, in this case, alpha on 2 minus beta on 2 times by omega. You guys can look at it. I encourage you guys to try out the maths yourself, because it's a good exercise. And some factoring out the front later on. Wait for my document to load. Not sure why it's doing that. By the way, do you guys know what a sinc is? Like the sinc function? Oh, there we go. So just factoring some stuff out and cleaning up a bit. So the sinc function, some of you might know, is just sine of x over x. So sinc x is sine of x over x. So I've chosen to write this in terms of sinc, well, just because the answer had it in terms of sinc. So I've got sinc of beta minus alpha on 2 times omega. And that's going to give me a beta minus alpha on the front. Again, I'm not going to go through the maths behind this. It's literally just algebra. You will get it the best if you attempt the question and you try and maths it out. Anyways, so that is the Fourier transform of W. Now, you can actually get a very similar result if you look at the rect function, which is what the alpha and beta signal was. It's called a rect function. I'm assuming rect for rectangle. If you look at the Fourier transform table, it does actually give you a sinc function. And then, so the last step I have there where I get to the answer. So remember, V of t multiplied by W of t. So multiplication in the time domain gives you convolution in the frequency domain. And we're going to convolve this function, this sinc function, with capital V of omega. And remember, capital V of omega we got as Dirac deltas, right? Because the cosine transformed into Dirac deltas, right? So all I've done there is I've just used the fact that convolving with a Dirac delta just frequency shifts the signal by a certain amount. In this case, because the Dirac delta was shifted by omega naught, then the function W also gets shifted by omega naught. So you end up with this really messy thing, which is actually very close to the original question, but I've replaced it's like omega naught is replaced with W plus omega naught, and likewise omega minus omega naught. That's the difference. That's my opinion on what the answer should be. You guys are welcome to try it out and see if you get the same thing. But I mean, it's a very hard question. Maybe it's not worth it. Maybe it's not worth your time. Maybe you're looking for a little bit of extra, like brain teaser. In which case, this question is, I would say I enjoyed doing it. I did go down a bit of a rabbit hole on like Dirac delta properties and like translation properties and stuff like that, and it was fun. I did verify all of the properties before as well on Wikipedia and other university websites. Anyways, but that's my opinion on what the final answer should be. Anyways, so I'm going to share that. I'm not sure whether we'll post it, where we're going to post it. I might just, you could just post it with the YouTube link. That might be useful. But I'm going to,
If not, it'll be in the Google Drive or places.
I can also like upload it on the Teams technically.
Yeah, you can do that.
Yeah. But yeah, I'll upload it now.
Okay, thanks so much, everyone.
Thanks. Thanks for sticking around. Yeah.
And best of luck with everything.
Yeah, no, I'm just uploading my formula sheet and the actual answers for today's.
Okay, and thanks to everyone watching on YouTube as well.
Yeah, thank you guys.
Bye.